Okay, here we go. And now let's take a look at the um, practice final exam. I'm going to pull this out a little bit bigger so that you can kind of see everything that's on there. Um, right in the beginning, uh, on the first page. Now the way I think this will work is I've got a header link. So up at the top of each page, when you pull it up on the final exam, there will be this link. If you click on that link, it'll take you to this page. Uh, it'll it'll just take you to show you like formula for density is that. There's the conversion from kilograms to pounds. Uh, there's the way you calculate percentages. Here are atoms with electronegativities. Here are the solubility rules that I had you memorize. Then there are some formulas over here that have to do with gas laws. Talk about bond types and polarity, and uh, so there's a whole host of information like that that's on the front of the exam. Now this is actually a copy off of the standardized final exam, and this is the kind of information that they give out on that. Then of course there's a periodic table that you can use here that will come up, and some other things. Value of R, we memorized it, but there it is in both liter atmospheres and joules. And then the conversion from atmospheres to millimeters and centimeters and kilopascals and 22.4 liters at standard temperature and pressure and so forth. So this information will be available to you on the final exam. Okay, so let's get started then at working through some of the problems. And well, let's look through it first. Now this exam is a little bit different, but the same kind of subjects. It's a little bit longer. There's what, 52 questions on this one. Your final exam has 40, but they're patterned after these. And your final exam, even though it's 40 questions fewer than this one, it's also more visual than this one, so that you can uh, look at pictures and graphs and things like that to get answers without having to do detailed calculations. So let's just go through and work through this one, and then we'll see if this sparks any questions that you have that you'd like to ask about to review for the final. Okay, I need to shrink this down a little bit more and put that down and put that down. Let's do stop the share now and start working the problems. And I'll go back and forth between them. The first one is a conversion problem, and we want to convert 2.8 times 10 to the minus 4 centimeters, and we want to convert that to centiliters. We want to convert that to microliters. Okay, now the way we're going to do conversions, this is within the metric system. So I've got 2.8 times 10 minus 4, and centim is 10 to the minus 2. So that's 10 to the minus 2 meters. That's 2.8 times 10 negative 4 centimeters. Now we're going to convert from meters to microliters. From liters to microliters. Well, micro is 10 to the minus 6. So when I do that conversion, I'm going to just 10 to the minus 6 divided by 10 to the minus 6 is just going to be 2.8. Now you see, this will show you also the way we do final exam. Sometimes, you see, if you set this up, you don't actually have to go to the calculator to do anything. You could write that answer down when you get to this stage right here. So that's sort of typical of the way final exams are done. Now, the second one is a more complex conversion. It's not as bad as the one we did on the review quiz. We want to go from pounds per gallon and we want to go to grams per cubic centimeter. Okay, so we've got our 8.46 pounds, and gallon is down here. Let's get rid of the pounds and go to grams. Well, pounds and grams, there's 454 grams in 1 pound. So at this stage now, we've got grams per gallon. Now and grams is where we want it to be. So let's get rid of gallons. And gallon is down here, so I've got to put it up here. And I'm going to go to probably quarts. And there's 4 quarts in 1 gallon. Now that's got rid of gallons. Now I've got gallons per quart. Now, I want to go from quarts, and I'm going to go to milliliters, because that's the factor I remember. 1 quart is 946 milliliters. So now I've got to grams per milliliter, and that's really where we can end, because milliliter and centimeter cubed are the same. So if I just do my math here, that should give me the answer. And I've got 8.46 times 454, and all the rest are ones. I want to divide by 4 and divide by 946. And that comes out, what I got is 1.015 grams per cubic centimeter. And the answer is 1.00. So that fits pretty close to what we had. And I don't know, I may have tweaked the number somewhere a little bit to get that. I knew when I started out that I need to get about 1, because I recognize that 8.46 pounds per gallon to be the density of water. And that's what we came out with, was 1. So that was a good exercise. Let's look at number 3 and see what it looks like. I think I can read it to you without having to go back over to the screen, and we can get the answer. The question is, it says the middle 10 columns. The middle 10 columns on the periodic table are designated as, and the choices are periods, metals, transition elements, or families. And of course, the middle, if you look at the periodic chart, it's like this. And then down here it's like this. And we're talking about this group of elements here. And that middle 10 is the transition elements. And so that's the answer to that one. Again, so you see, that's one that takes no time really to do. Okay. Which of the following compounds is identified or spelled incorrectly? So let's do a screen share, because you need to see this. Now, here's what I would probably do. I would look at this compound and try not to pay attention to the name over there and just see what I think it is. I would recognize PO3 as phosphite, and phosphite has a -3 charge. There's 2 of them, so that's -6. There's 3 cobalts, so that 3 has to be equal to +6. So that means the cobalt, each one is +2. So I would name this compound cobalt 2 phosphite. And look, that is an answer that's correct. I'm looking at the left-hand compound, this compound now, and I would name this diiodine monoxide, or diiodine monoxide. That's not correct. But it would be okay, because oxide is -2. Iodine in this position would have to be +1. And we could perhaps call it iodine oxide. Let's kind of keep an eye on that one. This one is silver chloride, but the chlorine is -3. That would be silver 3 chloride. If that was just AgCl, we would just call it silver chloride. This could be named silver 3 chloride. So that looks okay. And zinc, this is chlorite. Chlorite is -1. There's 2 of them, -2. Zinc is in its proper oxidation state as +2, and it doesn't need a Roman numeral. So these 2 are both correct. Now, this is the correct name for this compound. And I would prefer to name this one diiodine monoxide. So B is the one I would choose as being the one that's incorrectly named. Now, is it likely that you would have AgCl3 as a compound between silver and chlorine? Well, maybe not, but I am betting you could make it. So I think the naming is appropriate. The compound is perhaps not a likely compound, but you don't have that kind of experience to know which things can be made and which things can't be made, perhaps. So all we're looking at here is how would you name this compound? And if silver's n +1, you don't use a Roman numeral. But if it is something else than +1, you do. And that's the same true of all of those elements that we said we didn't use a Roman numeral. Zinc is always +2 in its compounds, but if you ever found it as a +1, you'd have to name it zinc 1 chloride or whatever. Okay, so this one is also typical of the way you would like to design questions. When you're designing a question, you would like to have some answers that could be easily eliminated. But what you want to get down to is 2 that's a little tighter choice. And that's what happens to distinguish the A and the B students. Those that are, just slightly different. And so that question is like that. All right. Now, the next one, I think we can get this one also without going to the pad, because we can look at it on here. The total number of atoms present in this formula. Maybe I'll take my calculator along with me and as we talk through it. So let's see how many nitrogens we would have. Well, we've got 3 ammonium ions, so that 3 multiplies by the nitrogen. So I'm going to say we got 3 nitrogens. Now, how many hydrogens do we have? We've got 12 here and 12 here. 12 and 12 is 24, so we'll add 24 to what we got for that one. How many phosphoruses? It's got 1. So we got 1, plus how many oxygens? We got 4 from here and 6 from here is 10. So if I'm counting this correctly, there should be 38. That's what my calculator says, and there is the correct answer, 38. So see, that's another important type of idea to carry from a course, is how do you interpret a formula in terms of the number of atoms of each kind that's in a formula. Now, how many oxygen atoms are in 4 moles of this compound? By the way, how would we name that? This is ammonium ion, this is phosphate ion. You call it ammonium phosphate. You do not call it triammonium phosphate. It's ammonium phosphate. Hexahydrate is the way we would name it. It's ammonium phosphate hexahydrate is the way we would name that compound. Now this one I think we might need the pad to do. So let's stop the share and how many atoms of oxygen are in, I don't know, maybe we can do it on here. We're down to number 6. And we got 4 NH3 PO4.6H2O. Now, let's look at the oxygens again. I'm going to take that 4 out like this and count what's inside. So we got 6 plus 4 is 10. That's what we said a while ago. So we got 10, and 4 of them would be 40, and that would be 4 moles of that compound. That would be 40 moles of oxygen atoms. A mole of anything is Avogadro's number. So it's 40 times 6.02 times 10^23. And if I do that number, I get 40 times 6.02 with an exponent of 23. And I'm getting 2.4041 times 10 to the 25 atoms of oxygen in the compound. Now, I do want to go back and screen share that with you because I want to show you something. We got one of the answers. We got this answer here, 2.41 times 10 to the 25th. But now, if I didn't have a calculator, I can eliminate 10 and I can eliminate C and D. How? Because this is moles. A mole of anything is something times Avogadro's number. Powers of 10 to the 24th or 10 to the 25th are pretty good, but these two answers I could eliminate. I maintain I could also eliminate that one. How could I eliminate that? I recognize that as 1 mole. I look at that formula and it's sure got more than 1 mole of oxygen in it. So without putting pen to paper, I could get this answer without ever doing a piece of work. I can eliminate those 2 answers because they're unreasonable. I can eliminate that answer because it's 1 mole, and I've got, well, we saw 10 moles for just the compound. So this is the only answer that would make any sense at all. So that's the kind of thing you also want to look for when you're doing your own final exam. See if you can find ways to answer the question without having to do anything, but just look at the question. That will save you time. Now, I don't think time is going to be the kind of issue on the final that it was on this last exam you just did, but any way you can save time, do it. Okay, now this is a balanced equation. Now, just for information purposes, if I'm looking through the test and looking at questions, when I have to balance an equation, I know that's going to take me some time. You know what I'm going to do? I would skip this one and come back to it. But we're not going to take that option now. We're going to write the equation and balance it. So when we combust methanol, CH3OH, Now that's the formula for it. I tell you what I'm going to write though. I'm going to write it as CH4O. Now that's not the formula for that compound, but by separating the two oxygens, two hydrogens like that in the formula, the way they really are, it kind of sometimes can make you make a mistake in the balancing. Now, what do you get when you combust something? That means you're reacting it with oxygen. What do you get when you react a compound with oxygen? You get the oxide of each of its elements. So we're going to get CO2. And what's the oxide of hydrogen? Water, H2O.
Dr. Pearson,
Yes.
can we see your paper?
Thank you. I see what I'm doing. Sorry. Here we go. So the formula of CH3OH, I'm writing it CH4O just so I don't get screwed up with 3 here and 1 there. This makes it easier not to do that. Okay, now I'm balancing the equation. When you combust something, you react it with oxygen. When you react a compound with oxygen, you get the oxide of each element. Carbon is going to be carbon dioxide. Hydrogen is going to be water. Now, this is my basic reaction to start with. How do we balance equations? Well, we look for the element that isn't balanced and appears in only one formula on each side. Well, carbon is balanced and with a 1 there, so that wouldn't be good. Hydrogen's got 4 over here and 2 over there. It's not balanced. Oxygen's in a lot of different formulas. So the choice would be hydrogen. If I want hydrogen to balance, I'm going to put an A in front of this formula. And now I have 4A, and that's a 2, so I'll need a 2A right there to balance hydrogen. Now, I put a dot there, I balance hydrogen, I put a dot there, and a dot here, because hydrogen is now balanced. So I should do either carbon or oxygen next. I can't do oxygen because I need 2 coefficients to do it. So the only choice is carbon. So if I've got A carbons here, I've got A carbons here. Now carbon is balanced and oxygen is dotted. Now we've got to a point where there's only one coefficient left and I'm allowed a second variable. So I'm going to balance this next equation, this whole equation, just by putting a B right there. Now, I tell you this equation is balanced. I have that coefficient, I have that coefficient, I have that coefficient, and that coefficient. So the equation is balanced, but now I need to balance the oxygen. On the left-hand side, what have I got? I've got A from here plus 2B from here. How many oxygens do I have on this side? 2A from here and 4A from here. 4A and A, yeah, and 2A. That's right. Okay, so on the left-hand side, I've got 6A. Right-hand side of A plus 2B. If I subtract A from both sides, I get 2B equals 5A. So B is equal to 5, and A is equal to 2. So if I go back up here now and rebalance my equation, this is a 2. This is a 5. This is a 2. 2A, this is a 4. So there are my balancing coefficients. And it says the sum of the coefficients in the balanced equation, to say some of the coefficients of balance and water to produce carbon dioxide and water is, so I need to add all these coefficients up. 5, 6, 7, 8, 9, 13 should be, whoops, 4, 5, 6, 11, I get 13. Let's double check and see if it's balanced.
Dr.
Carbon,
Pearson,
yes.
on the water, when you were doing the oxygen, you put 4A. Should it, like when you're balancing the equation, you put down 2A plus 4A down there. Should it not be 2A plus 2A?
You're correct. That's where I made the mistake, isn't it? Oh, thank you for catching that. It should have been 2A, and it should have been for oxygen, so that should have been another 2A. All right, let's back up and punt. So the right-hand side is 4A. So I have 2B equals 3A, right? And so B is 3 and A is 2. Okay, so it's still got 2, but this is a 3 instead of a 5. That's a 3. And that's still good, right? So I've got A is 2, so that's 4. And A is 2, that's 2. So 4, 5, 6, 7, 8, 9, 10, 11. Now we're good. So the sum is equal to 11. Okay. All right. So that's answer B for number 7. Thank you for catching that. Okay. But it also shows you how multiple choice questions can be written in a way that doesn't give away the answer. So you're never going to be able to, I'm never going to ask a question like, for example, the coefficient in front of water is 3, you know, because if I tell you it's a 3, and then you can go in there and try it and see if it works. That doesn't balance the equation. So I won't ask questions like that. I will always ask them in a way that doesn't give away the answer. An unknown compound, very explosive compound, is found to be 15.6% carbon, 83.1% oxygen, and 1.3% hydrogen. The molecular mass of the compound is 154. What is the molecular formula of the compound? Okay, now this is the way final exams are sometimes written. And I told you in the class, I'm not going to, I'm generally not going to ask a question like this because actually the answer is given away in asking the question. Molecular weight, we told you, is 154. So if there's a correct answer on there, it's got a molecular weight of 154. So let me see which one looks like it might be that much. Let's try C and see what its molecular weight is. It's 2 times 1.008, that's 2 hydrogens, plus 2 times 12.01, plus 4 times 16. No, that's just 90. Okay, let's try D. 1.008 plus 12.01 plus 4 times 16 is that, and then times 2. 154. We got it. That's it. So it's this one. And I'm not sure what that, okay, so it's got 2 carbons. I'm not sure what that compound is. It's really explosive. I thought it might be a different compound than what I'm seeing there. Okay, anyhow, I'm going. What's mass in grams? Now, if you wanted to go about doing that one, I mean, I can show you how to do it. Maybe I should. The way we've been doing. Okay, we've got a compound that is 15.6% carbon, and it's got carbon, hydrogen, and oxygen. So I'm going to say CX hydrogen Y O Z. So that's going to be my formulas. So percent carbon is 15.6. The percent hydrogen is 1.30. In the formula, the carbons, I've got X of them, and that's times 12.01. And I've got Y hydrogens, and that's 1.008 for its molecular weight. So if I cross multiply and run through, I get 15.6 times 1.008 is 15.7248 Y equals, percentage of cancel, that 12.01 times 1.30, 1.30 times 12.01, that comes out to be 15.613 X. So 15.7, 15.6, that's essentially 1X equals 1Y. So X and Y are each 1. So my formula is C1H1OZ. So if I ratio carbon to oxygen, we can get that one. So we want 15.6 for the percent of carbon. Percent of oxygen is 83.1. The number of carbons is 1. Atomic weight is 12.01. The number of oxygens is Z, and the atomic weight of oxygen is 16. So again, cross multiply, 15.6 times 16 is 249, up here, 0.6 times Z equals to 83.1 times 12.01, 83.1 times 12.01. Yep, I'm just checking my numbers to be sure. All right, and that is, oh gosh, now I got a place to put it. 998.031 is equal to 249Z. So if I divide that number by 249.6, so divide that by 249.6, I come out with 3.998. So Z is equal to 4. So it's CHZ, CHO4 is the compound formula. And by the way this is structured up there, I can eliminate the others. The only one now that's left is D. And what I would do is figure out this molecular weight. Molecular weight of that thing would be 12.01 plus 1.008 plus 4 times 16. Molecular weight of that is 77.018. And now, if I look at the molecular weight, it's 154. So if I divide 154 by that answer, it comes out 2. So it doubles the formula. So that's the way you would work it from scratch if you didn't notice that given the molecular weight and possible formulas, you can figure out which one works. That's the only one that works. And that's the way you can do that problem. So again, there's more than one way to work any problem. Some of them are quicker than others, and you would really like to get to the answer in the shortest time possible. Well, I'm about to run out of paper here, so we're going to have to finish this course. All right, let's see. We are at, what is the mass in grams of 3 molecules of fluorine gas? So um, mass, grams, 3 molecules, fluorine gas. That, again, depends on you knowing it's F2. Okay? All right, so how do we get that? We're going to just convert from molecules to grams. So I've got 3 molecules, and I'm going to convert from molecules, and I'll remind myself it's F2, to grams for F2. Now the question is there a number of molecules for which we know the mass? Yes, a mole, Avogadro's number. So 6.02 times 10 to the 23rd molecules would be 2 moles of fluorine, and that's 2 times 19. Molecular weight of fluorine is 19.0. So 3 times 2 times 19 divided by Avogadro's number should give us our answer. 3 times 2 times 19 divided by 6.02 with an exponent of 23. So I'm coming out with 1.89 times 10 to the minus 22. And that's going to be response A, but I want to share with, I want to go to the screen again and make another quick point. Okay, here's my 2 answers. I'm looking up here and mass of 3 molecules. Molecules are extremely tiny, so they're going to have very, very tiny amounts of mass. I can eliminate B and C immediately. There is no way 3 molecules of anything could weigh 38 grams. I mean, imagine what the mass of a mole would be. Take 38 and multiply it by Avogadro's number. Huh? Well, that's not possible. These 2 are not possible. Either one of these 2 is. So I do have to do the math in order to distinguish them, and I don't see any way to tell which one is which. So we had to do the math on that part of it. But if I had done this and said, I'll go through this and I'm on my last pass and I'm running out of time when I go back to recheck, I'm going to just guess between these 2 if I don't have time to work it. I can eliminate those 2. So, 50-50. I don't know which one would be which. Okay, while we're here, we'll look at this one, then we'll go over the scratch paper. 50 milliliters of 6 molar hydrochloric acid is added to 250 milliliter volumetric flask and diluted to the mark. What is the final molarity of the gas? So let's go over here and we'll work that one out. We've got 50 milliliters of 6 molar HCl. We put it in a volumetric flask and we're going to take it to a new volume of 250 milliliters. And we want to know, what would that new molarity be? Well, remember what we did? We had volume times molarity. Volume times molarity is moles. So the volume of this concentrated times the molarity of that concentrated solution has to equal the volume of the diluted solution times the molarity of the diluted solution. Now, I've got my volume, so I can do that. I can say 50 milliliters times 6 moles per liter is going to be millimoles. That's going to have to equal to 250 milliliters times this new molarity. Now, I want to set it up like this so you can see if I keep the same volume unit on both sides, I don't have to convert to moles. To liters, because there's 50 milliliters and there's 250 milliliters. The volume cancels out. So if I did 250 times 10 to the negative 3 and 250 times 10 to the negative 3, the 10 to the negative 3s would cancel on both sides. So the important thing about this is to keep the same volume unit on each side. That'll save some time in doing the math and maybe some potential mistakes in converting to moles every time. Okay, so let's do it. It's 50 times 6 divided by 250. So we're getting 2.024 as our molar mass, and that's close enough to be 2.02, 2.00 is what it's showing here. But let's see, did I do it right? Oh, wait a minute, maybe I didn't. It's 50 times 6 divided by 250. Oh, no, I did do a key punch wrong. It's 1.20. That was unfortunate. I got an answer that was pretty close to that answer, but it sparked me to know it should have been plus or minus 1 in the last significant digit. And I was off by 2 in the last significant digit. I pushed the wrong button. Okay, now let's go back to screen share so you can see the quiz. We're at number 11. Yeah. Okay, what do we got? It says, which one of the following nuclide symbols correctly represents 25 protons, 23 electrons, and 30 neutrons? So number 11, 25 protons, 23 neutrons, and 30 electrons. No, I got it backwards. I thought that didn't make any sense. 23 electrons and 30 neutrons. Okay, I've got the data down. Let's go over on the scratch page and see where we're at. Okay, we got 25 protons, 23 electrons, and 30 neutrons. The number of protons gives us the symbol. So I'm going to have 25 as my lower subscript. There's 3 of the answers that has that on it. And that I would look up on the periodic table just to be sure. From the answers, it has to be manganese. But I look at it, sure enough, manganese is the 25th element. So it is manganese. Well, let's see what isotope it is. I've got 30 neutrons and 25 protons. That would be 55, right? 55 neutrons. Okay, so we got a 55. That eliminates one of those 3 that we had. Now we're still left with A and C. Oh, I just see something I didn't. Wow. Okay, I'll show you in a second. Now, what is the charge number going to be? Well, it's got 25 positive charges. It's got 23 negative charges. So the charge has to be plus 2. Okay. And guess what? Let me show you. Okay. Both A and C are the same. Let's go down and see what the answer is supposed to be and fix it. because I know the other one that should have been there. Which one was number 11? We said the correct answer is A. So we'll leave that one alone. Now, what probably should have happened was to calculate the charge number by opposite. So instead of having a +2, a -2 would have been a good FOIL. So let's do that right here. Now, yeah, let's make that 2 minus. And voila, I'll save it. We fixed it. Now that is the correct answer. Okay, now, next one is, next several it looks like. Oh, no, we're not there yet. Next one has to do with the amount of potassium in a compound. So I think I can duplicate this for you on the pad. So 12, it says how many grams of potassium are in 25.0 milliliters of 0.455 molar potassium phosphate, K3PO4. That's the question. Here's what we're given. 25 times 10 negative 3 liters, that's 25 milliliters. The molarity of that is 0.455 moles per liter. So this is going to be the moles of the compound. So we can go ahead and do that math, I guess. 25 with an exponent that's -3 multiplied by 0.455 gives me 0.011375 moles of the compound. Now I want to convert from moles of the compound to grams of potassium. Yes. Now, 1 mole of the compound has what? It has 3 moles of potassium, and that's 3 times the molecular atomic weight of potassium. Let's see what that is. 39.1. Yes. So it's 39.1. You know, every once in a while, something flies across my brain that I find interesting. The potassium, you know, if you look at the periodic table and look at the molecular weights, generally the bigger the atomic number, the atomic number, the heavier they are, the further you go down. If you look at potassium, it's 39.1. If you look at argon, it's 39.9 something or other. Again, I'm trying to, 39.948. Argon is number 18 and potassium is number 19, but argon is much heavier than potassium. So their chemical properties definitely define they have to be in the formula in the families they're each in, but their order of atomic weights is reversed to what you expect. Now, why does that happen? Well, that happens because almost all of the noble gases come from radioactive decay of heavy elements. That's where those things come from. And if you think about it, when something is unstable and it decomposes, it's radioactive, it's going to make something much more stable. And the thing that's much more stable is the noble gases. So it's not surprising at all when you think about it that you would make noble gases as some of the end products of the radioactive decay of uranium and the heavier elements after it. And when you do that, it turns out that the argon you make is heavier than the normal, most stable isotope. You make one of the heavier isotopes that's stable, but it's not as stable as some of the other isotopes of argon. And we make use of that to get an age of the universe. That discrepancy between potassium and argon led us to discover how old the Earth is, or how old the universe is. Anywhere it's got potassium and argon in it. So I thought that's kind of interesting that there is that little nugget left right out there for everybody to see that allows us to put an age on the universe. I think that's interesting. All right. Somebody wants us to learn something. Okay. All right, then number 13. Oh, did I give an answer to that yet? I didn't work out the answer, did I? Okay, so I got this number. I need to multiply it by 3 and multiply it by 39.1. And that should be it. And I'm getting 1.33. My answer up here is 1.3342, whatever. So 1.33 is response C on the exam. Okay. The next one has to do with chemical reaction. So there's 3 of them, I think. No, 1, 2, 3, 4, 5 problems that deal with this. And the equation we're using is 2 AlNO3s, 3. That's aluminum nitrate. It's going to react with 3 K2CrO4. That would be potassium chromate. It's going to make Al2CrO4 3 and 6 KNO3s, potassium nitrate. Okay, so those are the things involved in the reaction. And it says the number 13 is how many milliliters of the aluminum nitrate. Okay, so I want to know how many milliliters of this molarity is 0.832. That's the molarity of the aluminum nitrate. Would be required to react with 50 milliliters of 0.208 molar chromic acid. Now, volume times molarity is moles. So the equation is showing 2 moles. Volume times molarity is moles. The equation is showing 3 moles. So this is my rebalancing factor for the potassium chromate and governs how much of everything that is used. So my RBF is going to be 50 times 10 to the minus 3. That's volume in liters times 0.208 and divided by 3. My answer in moles of the aluminum nitrate is going to be my rebalancing factor, that one, times 2 moles is what's shown in the balanced equation. So I can do this math, and then we'll complete the problem from there. So it's 50 with an exponent that's -3 times 0.208 divided by 3. That's my rebalancing factor, times 2. And I'm coming up with the number of moles is 0.006933, repeating decimal, moles of aluminum nitrate. Now, that's equal to the volume we need times the molarity of the solution. It's 0.832. Yeah. Okay. So if I want to solve for the volume, I take this number that I just got on my screen and I divide it by 0.832. So I want to divide that by 0.832. And I come up with 0.00833, repeating decimal, liters of the solution. I need to convert from liters to milliliters. Milli is 10 to the -3. So I need to divide this number by 1 times 10 to the -3 to get it into milliliters. So I'm dividing that number by 1 with an exponent of -3. Got a oh, I see it's way back up here. I put 50 milliliters there. That's supposed to have been a 55. Okay. No big deal. Let's just go back and run it through. This will be 55. Now let's do the math. It's 55 times, okay, 55 exponent -3 times 0.208 divided by 3 is that. Now I've got a slightly different number for this. I need to multiply it by 2. And then that gives me a slightly different number for that. I need to divide it by 0.833. And that gives me a different number. And then I need to divide that by 1 with an exponent of -3. And I come up with the volume is 9.11556 digits. So it would be 9.16 milliliters would be the correct answer. Okay. And that is response D on the test. How many grams of aluminum chromate can be produced from 125 milliliters of 0.15 molar? So I'm going to go back up here and get my equation. And I'm only going to get the things I want. I want the aluminum, I want how many moles of aluminum chromate? I want potassium chromate. So this is number 14. The potassium chromate is 2K2CrO4. And it's going to go to aluminum chromate. It's 1Al2CrO4. 3. Okay. And we want to know how many grams of this, how many grams will I make from 125 times 10 minus 3, 125 milliliters, and the molarity of the solution is 0.150 moles per liter. That product is moles, the equation showing 2 moles. I want the molecular weight of this compound. There's 1 mole in the balanced equation. Molecular weight is given at 402 for the molecular weight of this compound. Now, if I take that number and that one divide by that, that gets the rebalancing factor. So it's 125 with an exponent that's -3. I need to multiply it by 0.150 is the molarity of the solution. I want to divide by 2. That's the balancing coefficient. And the rebalancing factor, I have a number on my screen. It's 0.009375. And now my answer is going to be that number times this number. So the answer is the RBF times the 402 grams of the aluminum chromate. So multiply that times 402, and I get something that looks funny. Let's try, what did I do? 125 with an exponent that's -3. The molecular
There's a
weight.
3 in front of potassium chromate.
I'm sorry? What did it
There's
say?
supposed to be a 3.
Yeah.
There's supposed to be a 3 in front of potassium chromate, not 2.
Oh, well, where did I get that? Here, oh, I was probably looking at the wrong formula. Thank you. That fixes it. It's going to make that different, but let's see what we get now. Thank you. Let's do it. It's 125 with an exponent that's -3 times 0.15 divided by 3. That should give us the rebalancing factor is 0.00625. Now multiply that times 402. And that looks a little better. That gives me an answer of 2.5125. 2.51 grams then would be the correct answer. And that is response D. Okay. And now we're at number 15. We got 2 moles of the aluminum nitrate react with 5 moles of potassium chromate. What is the number of moles of aluminum chromate and potassium chromate? So we're going to do both of them. Let's go back, get to my balance. There's my balance equation. Oops, right there. And we've got aluminum nitrate, and there's 2 of those. And we're reacting it with the potassium chromate, and there's 3 of those. Now, we want the total number of moles of product, and that's 1 plus 6 moles of product. That's what it's asking. So let's look at the numbers. We've got 3.5 moles of the aluminum nitrate. Yes. And we've got 5 moles of the potassium chromate. The equation balancing coefficient is 2 moles here and 3 moles here. So my rebalancing factors, I've got 2, is 3.5 divided by 2. That's 1.75. And 5 divided by 3 is 1.66 repeating factor. So it looks like that's the limiting reagent. And if I take that and multiply it by the total number of moles of product, that should give me my answer. So times 7 should give me my answer. And let's see which one that is. 11.7 is A. We got 11.6666666. 11.7 is response A. Number 16. If this many grams of aluminum nitrate is reacted with excess potassium chromate, how many moles of potassium nitrate would that produce? So again, I'm reacting aluminum nitrate, and we had 2 Al2NO3s. And now potassium nitrate is what we're making. And how many of those did we make? 6. No. 6 KNO3s. Okay, so now let's look. I'm having a. Okay, here's the problem again. So I'm reacting 355 grams of this. And how many moles? The equation shows 6 moles. The equation is showing 2 times the formula weight of potassium nitrate. No, aluminum nitrate, it's 213. So there's my rebalancing factor. So my answer is going to be the rebalancing factor, which is 355 divided by 2 and divided by 213 and multiplied by what's under my question mark over here is 6 moles. So that should be the answer to that one. Get where I can see the answer. Doing 16. Okay, so 355 divided by 2 and divided by 213. That gives 0.833 multiplied by 6 is 5. So this comes out to be 5.000 is what I get on my calculator, moles. And that is response B on the test, so we're good. And now this one, number 17, is going to work on the same equation. And it says how many grams of aluminum nitrate is required to produce 205 grams of potassium nitrate. So it's the same two things, 2 Al2NO3, 3. It's going to go to 6 KNO3s. And we want to make 205 grams of this. 205.5. The equation is showing 6 molar mass of potassium nitrate. It's off my screen. It's 111. And now, what did it ask us about the aluminum nitrate? How many grams? So I want to know how many grams. The equation is showing 2 moles, and the molecular weight was given way up there also.
Dr. Pearson, can you move your paper down a little bit?
Yes. Yeah. There you go. And the molar mass of the aluminum nitrate is 213. So there's my rebalancing factor is going to be 205.5 divided by 6 and divided by 111, and then multiplied by what's here is 2 times 213. Now let me see that it looks like I've got everything set up correctly. Let's go back down there and look at the problem again. 17. Okay, we had 205.5 grams of potassium nitrate. Balancing coefficient was 6 and its weight was that. We wanted to know the grams. Yes, that looks like that'll do it for us. 205.5 divided by 6 and divided by 111, multiplied by 2 and multiplied by 213. I'm getting 131.44 and some more digits. And 131 is the correct answer for A. That should be A. Okay, so we got it. Now we got 18. We got 18, 19, 20, 21, and 22 with a different equation. Okay? 18, 19, 20, 21, and 22. And it's got all kinds of stoichiometry in it. So the equation we're going to be using for all of them is 20 NO2s and 3 C3H8 goes to 10 N2Os and 9 CO2s and 12 waters and minus 5970 kilojoules is the heat flow. So it looks like this is going to have gas, liquids, all kinds of stoichiometry. We got 5 questions on it. So number 18 is how many liters of N2O at 20 degrees C and 1.5 atmospheres pressure would be needed to produce to produce how many liters of this can be produced from 2.50 liters of C3H8 at 25 degrees. That was 25 degrees up there too. At 25 degrees C, and what's the pressure? 1.5 atmospheres. Okay, now this is a good one. Now it's gas stoichiometry, but notice the temperature and the pressure is the same. Now that makes the problem a lot easier. How many liters of NO2? So the N2O, we've got 10 N2O, and it's formed from 20 NO2s and 3 C3H8. Now in this problem, we need the C3 and H8, so I didn't need the 20. Okay, but now here's what the problem says. Problem says, how many liters of the N2O can be made from 2.5 liters of the propane? Now, if they're at the same temperature and pressure, 3 liters of this form 10 liters of that. So if I've got 2.5, then I can just do my rebalancing factor like this, and this is going to be the easy problem. It could have been tough, okay? So if I take 2.5 and divide by 3, that gives me the rebalancing factor, and multiply it by 10, and that gives me 8.33. So I'd make 8.33 liters. As long as that they're at the same temperature and the same pressure, you can use the balancing coefficients as if they were liters instead of moles. That was Gay-Lussac's law of combining volumes. And we saw that to be the case. So if you recognize that here, it saves you a lot of time. If you didn't recognize that, you could convert all the liters to moles and then work the problem like a regular gas stoichiometry problem. We may have one coming up right now on 19 that we have to do that. How many liters of NO2 at that temperature and pressure? So how many liters of NO2 at 20 degrees and 1.5 atmospheres, now that's a different temperature, is required to produce 30 grams of CO2? So I'm looking at my equation. I've got 9 CO2s on the right. And the other thing we're dealing with is the NO2. And I've got 20 NO2s on the left. So those are the only two things I'm doing. And I want to know how many liters at some T and P. Over here, I've got 35 grams. And the weight shown in the problem is 9 moles. The molar mass for CO2 is 44. So there's the rebalancing factor. The equation is showing 20 moles. So I can solve this first in moles, and then I'll get the answer from the ideal gas equation. So I've got 35 divided by 9 and divided by 44. Yes. So there's my rebalancing factor on my screen. I multiply it by 20. And what I come out with is I'm going to have 1.7676 moles of NO2 that I'm going to need. Now, volume times pressure, PV equals N RT. So V is going to be N RT divided by P. Now it's a matter of plugging in the numbers. Volume is going to be N, which is this number I've got here. R is 0.0821 liter atmospheres per mole per Kelvin. And the temperature is 20 degrees Celsius. So that's 20 plus 273 divided by the pressure. Pressure is given at 1.5 atmospheres. Okay, so I've got my numbers. The number of moles is on my screen. So it's times 0.0821 times the left parenthesis 20 plus 273.15 close divided by 1.5. Okay. Well, I've got a little bit off somewhere, but I think it has to do with the, may have rounded off that. But the answer I'm getting on my screen is 28.4. The answer in the book they say is 20, I mean, it shows 28.8. Let me double check number 19 and see if that is the answer they have. If it is, I'm not worried about it. 19, it says is C. I think that's correct. Yes. Okay. So the difference could have been made by either rounding off the R value or rounding off the number of moles, but that's close enough for us. Okay, number 20. If that many kilojoules of heat are produced during a reaction, how many grams of CO2 was also produced? Well, these types of problems maybe look a little harder, but they actually are not. They are much easier. So I've got 9 CO2s. If that reacts or was formed, the heat involved was minus 5970 kilojoules. And let's see, we have 3,500 kilojoules in the reaction, and it was produced, so it's a negative 3,500 kilojoules. And we want to know how many grams of CO2 would have been produced. Well, the equation is showing 9, molecular weight is 44 grams. So if I take 35 and divide 3,500 and divide by 5970, that's my rebalancing factor. So 3,500 divided by 5970. Rebalancing factor is 0.586. So I'll multiply that times 9 and times 44. Oh. And then multiply that by 9 and times 44. Now let's see what that looks like. 232. Yeah, it comes out to be 232. That's showing 232.160884. So 232 is response B. So we're good. Now, number 21, I'll reproduce over here. It says we've got 23.0 grams of NO2, and we got 10 grams of C3H8, and we want to know how much heat, and so how much heat, the number of kilojoules. So this becomes a limiting reagent problem. The NO2 had a balancing coefficient of 20, wasn't it? Yes. So we've got 20 NO2s and 3 C3H8. The equation says that will produce negative 5970 kilojoules. The problem is got 23 grams here. The equation showing 20 times 46.1. This one, 21, 10 grams. The equation is showing 3 I think the molecular weight of that is also 44.1. Okay, so there's my two rebalancing factors. Let's see which one is smaller. So we had 23 divide by 20 and divide by 46.1. So one of my rebalancing factors, this one, barely got room. I can scribble it right there. 0.0249. 0.0249 and some other digits. Now let's do this one. 10 divided by 3 divided by 44.1. That's 0.075. 5 and other digits. So this one's got to be my limiting reagent. And so, like I said earlier, I can't get back up there to that spot on my screen, so I'm going to recalculate it. 23 divided by 20 and divided by 46.1. 0.0249. Yeah, I got that answer a while ago. Now I want to multiply that by times minus 5970. So I'm coming out with minus 148 point. This comes out to be minus 148.926 and other digits. So minus 149 would be the heat involved in that reaction. And that's response A on that test question. Good there. Okay. Gosh, you guys are still hanging in with me. All right. And I'm going to keep on going now because I don't want to lose any time. I want to get, okay, here we go. Now, number 22, I was about to miss it. It's how many moles of water can be produced from 14 moles of C3H8. Okay, let's get back up there where I can see my equation again. The C3H8, there was 3 of them. And the water, there's 12. And we got 14 moles of this one. The equation is showing 3 moles. And we want to know how many moles of water. And the equation is showing 12 moles. There's the rebalancing factor. The answer is going to be the rebalancing factor. It's going to be 14 divided by 3 times 12. That should give us the answer. I get a big number, but I think that's right. 56, yep. And 56 is B also. 23. That may be the last one with these problems. Okay, so we've really got every kind of stoichiometry represented that you can imagine. Okay, all right, we got a sample of an unknown gas occupies a volume of 50 milliliters at 100 degrees C and 500 millimeters of mercury. Calculate the molar mass of the gas. Okay. I'm seeing some numbers over there that don't look possible, so we'll comment about that when we get our answer. Now, we have P, we're going to treat it like an ideal gas. PV equals nRT. And now, the number of moles is the number of moles is going to be the grams of the sample divided by the molar weight of the compound. So let's rearrange this a little bit to try to calculate what we want. We got the pressure times the volume is equal to the mass of the sample divided by molecular weight times R and times T. Now, if I want to solve for molecular weight, I'm going to multiply through by it and divide by that. So molecular weight is going to be GRT over P and V. That's G. Okay. I think we got it calculated correctly. GRT over PV. Okay. Now we can plug in our numbers. The mass of the sample is 0.0185 grams, 0.0821 for R. The temperature is 100 degrees C, so that's 373 degrees Kelvin. The pressure is 500 divided by 760, and the volume it occupies is 50 times 10 to the minus 3 liters. Now, while the math is not terrible, it's still kind of messy. Molecular weight. Now, let's see. This is in the denominator of the denominator. So I'm going to simplify it a little bit to make our calculations a little nicer. Now I'm going to move this upstairs, 760. And now I'm going to put 500 and 50 times 10 minus 3. Now, that is a little nicer looking for calculational purposes. So 0.0125 wait, where am I? Where did I get that? That's supposed to be the mass, and that's not the mass. I am looking at 23. Where did I get that number? Well, I don't quite know. It's 0.0185 gram sample. Okay, 23. Yes, I'm looking at number 23. Okay, so 0.0185 times 0.0821 times 373.15 times 760 divided by 500 and divided by 50 with an exponent of minus 3. Okay, when I do all of that, what I came out with was 17.229 blah, blah, blah. So 17.2, that is response D, but I want you to look at it, at my answers. It's not necessarily our answer is going to be realistic. Remember, we're just testing concepts, but there is not going to be any molecule in the world that has a molecular weight of 0.02. So that answer is certainly not logically possible. The smallest thing is hydrogen gas, and that's H2. And for a mole of it, that would be just, I mean, lowest molar mass you can get is H2 off the periodic chart. So, and its molar mass would be 2 times 1.008. So that's not a possible answer. These other two answers would be possible, maybe. I mean, this is close to helium, and I don't know. I don't think we got anything at gaseous at that pressure, at that molar mass either. So if I were forced to guess, I would guess D without ever trying to do a calculation. But like I said, it is possible to make up numbers that are hypothetical numbers, but follow a principle we're trying to follow. So if you just put down some random numbers and didn't pay any attention to reality, then all of those would be possible. But in reality, D is the only one that makes any sense, really. Okay, while we're here, let's look at 24 and see what we're doing. 24. 2 moles of helium diffused through a hole in 32 seconds. 2 moles sample of an unknown gas diffused through the same hole in 64 seconds. Determine the molar mass of the unknown. Well, this again is a Graham's law type problem. V1 over V2 is square root of M2 over M1. And so let's make the oxygen here our known gas.
Am I back, Dr. Pearson?
Yes, thank you. I will. There we go. I'm going to make the oxygen the gas 1. So the velocity of the oxygen, let's see, we got numbers. We got 90. We got, oh, I'm sorry. I said I'm looking at 25. I should have been looking at 24. It wasn't oxygen, it's helium. This is helium. So I'm going to make helium my known one, number 1, and my unknown one, number 2. Now, so the velocity of the helium is 2 moles in 32 seconds. The velocity of my unknown, it was 2 moles, and it was in 64 seconds. So we got this complex fraction to deal with, but essentially the 2 moles are going to cancel. The 64 is going to go on the top and the 32 is going on the bottom. So I get 64 on the top and 32 on the bottom is equal to, now the helium was the denominator. So helium's atomic weight is 4. And this one we don't know. So molecular weight over unknown. So if I square both of these sides, square that and square this, then what I get on the right-hand side is molecular weight divided by 4. And this I'm going to do. So if I do 64 and divided by 32, I get that number. And now I need to square it. And of course, that's going to be a 4. So what I'm going to wind up with is 4 is equal to molecular weight divided by 4. Molecular weight is equal to 16. That's a possibility, and it is an answer. It's A. So that's okay. Temperature of a 90 milliliter sample of oxygen is decreased from 750 to 375 kelvins, both of them, as the applied pressure is increased from 1 atmosphere to 4. The new volume of the gas would be. So what we're going to do is we're going to do a P1, V1 over N1 and T1 equals P2 and V2 over N2 and T2. This is my initial state, I'll say. And this is final. Okay, so let's put numbers in. Okay, we're 25. I didn't write it down. Okay, there it is. Okay, now we had 90 milliliters of oxygen. I don't care what it is really. So let's make volume 1 is going to be 90 milliliters. The temperature is decreased from 750. So the initial temperature over here is 750 kelvins. And the applied pressure is increased from 1 atmosphere. So over here it was 1 atmosphere. And over here it's going to be 4 atmospheres. The new volume is what we want to find out. The temperature, we said, goes from 750 to 375 degrees K. And now, if I've got this oxygen, that's all I've done to it, the number of moles here, N1, will equal N2. So they'll cancel. And so it looks like I can solve for my answer. I can take cross multiply 1 times 90 times 375 is going to be equal to 4 times 750 times V2. So divide both sides through by 4 times 750, and I get V2. So V2 would be 90 times 375 divided by 4 and divided by 750. And I am coming up with a V2 equals 11.25, and in the same units that this was, so that'll be milliliters. And that's A, response A. A is 11.2.
Dr. Pearson,
Yes.
you could cross off the n's in that equation.
I'm sorry, I didn't quite catch you.
How could you cross out the number or the n?
The number of moles, because we've got this sample that's just oxygen, and we're changing conditions on that sample. See, it told us we had a sample of that. So the number of moles is not changing. If I wanted to change the number of moles, I would have said also the number of moles, we added so much or we took out so much oxygen in going from one state to the other. So you'd have to be given information different from that. But the assumption I made was we had this 90 sample, 90 milliliter sample at one temperature and pressure inside of some container. We took the pressure from 1 atmosphere to 4, pushed that down. We changed the temperature in it, but we didn't let any gas escape or put any more in. So that's why I canceled out the number of moles. It was a sample that we did something to, and we didn't do anything to change the number of moles in it.
Okay, thank you so much.
Sure. 26. We've got a sample of iron, and we're using the calorimetry equation. Q is mass times specific heat times temperature change. Okay, the sample weighs 425 grams. Now let's look at the specific heat and be sure we're good. Yeah, the specific heat is 0.449, 0.449, and it's joules per gram per degree Celsius. and the temperature change, and a simple, and we've dropped it into what its temperature was 99.5, and it's going to decrease its temperature to this value T. I don't know yet what that is. Let's see if it's information given. Yes, we dropped that into a sample of water, and we don't know how much water, but we do know one important piece of information. The water was at 19.3 degrees, and once it was done, everything was at 35 degrees. So I do know what the T was. It's 35.1. Now, we want to get the heat change for the iron. Well, now I got all the data. I could get it for the water. If I look up the heat capacity of water, I could figure this out, everything else, but I don't need to. I got 425 times 0.449 times 99.5 minus 35.1. And I'm calculating, I'm coming out with a big bunch of joules, so I'm going to divide by 1,000 to get to kilojoules, because I see that's what I got my answers in. So the answer is 12.28913 kilojoules. It's going to be 12.3 kilojoules. But now, what sign do we attach to it? If the iron got colder, the heat came out of the iron, right? So coming out is negative. So the sign is negative. Now, we didn't get forced into that problem here because all four of the answers, let's go back and look at it so you can see it. See, all four of the answers are negative. But if I had to apply the sign, I would have to do just what I did. If the iron's temperature went down, heat came out of the iron. Heat coming out is negative. So we would have gotten the correct sign. The FOIL for that would have been one of the answers be plus 12.3. And then that would force the issue. All right, 27. Given the following equations, standard enthalpies of formation, determine the enthalpy of formation of Fe2O3. Well, I mean, it's still what we've done before. Let's I'll stop the share so that we can do this. Okay, we've got iron. We've got number 27. We got 2 irons and 3 CO2s goes to Fe2O3 plus 3 CO gas. Okay, so by the way, the reverse of this reaction is the way we make iron from iron ore. Here, that's aside. Okay, now the heat of this reaction, delta H of that reaction, is going to be equal to the delta H of formation of Fe2O3 plus 3 times the delta H of formation of CO minus 3 times the delta H of formation of CO2. It's products minus reactants. I leave out the iron because it's an element in its standard state, so it's okay. I'm given the delta H of the reaction. It's plus 26.7 kilojoules for that reaction. Now, this is the unknown. This is what we are asked to calculate, so I'll just put an X for it. plus 3 times the delta H of formation of CO. That's given in the problem. It's minus, that's 3 times minus 110.5. And then minus the CO2 value is minus 393.5. So that's minus a minus 393.5. So I guess what I'm going to do is combine all of this and then do something with it. So I've got plus 26.7 kilojoules is equal to my unknown, what I'm trying to find. And then 3 times this negative, and this negative times this negative is a positive. Here's a case where I'm going to know that this sign over here is plus, and this sign here is minus. So I'm going to take this number and subtract that number. So it's, and there's 3 of them. So it's 3 times 390, it's 3 times 393.5. That minus and that minus makes this a plus now. And then I want to subtract off minus 3 times 110.5. So what I've got on the right-hand side is plus 849 kilojoules. So I want to take this, I want to subtract 849 from each side, and I'll get the X. So the unknown is going to be this number minus, so it's 26.7 minus my answer that I just calculated. And that's minus 822.3. And that is D on the test. So it's just a little different way of doing heats of formation of reactants and products. Calculate one you don't know. Okay, 28. Unknown substance found in chemistry laboratory, identify the substance. It's a metallic solid at 25 degrees and 1 atmosphere pressure. It melts at 1863. Its crystal structure is a unit cell is body-centered, and atom from the substance forms a +3 cation containing 21 electrons and 31 neutrons. The solid reacts with HCl to produce hydrogen gas and chlorine. I didn't write this question, but I like it. Okay. We got all kinds of stuff like you might find. The problem is, how do you sort through to find out what's important? And it's that little phrase in the middle there. An atom of the substance forms a +3 cation, so it forms a +3. That means it's going to be in either group 3, A, or 3B, because those are the ones that form +3 ions. The +3 ion has 21 electrons. Okay, that means the atomic number is 3 bigger than that. So that means the atomic number of that element is 24. Okay, I kind of bet you we can get the answer right now. All we got to do is find element number 24 on the periodic chart. We got to be there. Element number 24 is chromium. There you go. We got it. Okay, so that looked kind of bad going in, but it wasn't bad after all. Okay, rank the following. Oh, I see. I moved that column down a while ago and I caused some things to make it hard to read. Wow. Wow. Okay, now I can read the question. Rank the following in order of decreasing size. So I've got Cl minus, I've got K plus, and I've got argon. Now, Cl minus, if you look on the periodic chart, you add one more electron to it. Cl minus has the same configuration as argon. If you take one electron away from potassium, it'll have the same configuration of argon. So now this tells us the answer to the question. All of them have the same number of electrons, the same number as argon. I think that's 18, but the important thing is it's the same number. Okay, now, if they got the same number of electrons, then the one that has the most protons in it is going to be the smallest of the bunch. So the positive ions are going to be smaller than the neutral. And the neutral is going to be smaller than the negative ions. That will always be true if they've got the same number of electrons in each one. So I can rank these already in terms. The smallest one is the K plus. And the largest one is Cl minus. And the argon is in between. So that would be the order: K plus less than argon, less than Cl. Oh, okay, they're doing decreasing size, so I got to go the other way. So Cl minus is greater than Ar, and that's greater than K plus. At decreasing, I didn't pay attention, did I? So Cl minus and argon and K plus, that'll be response B on the test if you look at that. Which is the 29, ready for number 30. Which of the following atoms would have the largest first ionization potential? So we're looking at the elements Te, that's A, and B is bromine, and C is indium, and D is gallium. So we're going to have to look at those on the periodic chart and see where they are. And we're looking for first ionization potential. So let's first locate where they are on the chart. We're looking at tellurium. Te is this element right here. So maybe I'll make a check. That's kind of a sketch on this chart. Let's say Te is going to be right there. Now, where is bromine relative to Te? Bromine, okay, so let's do it this way. Te is right there, and bromine is this element right here. And indium is right there. So relative to Te, it's 3 elements over, so it's and it's the next one. So indium is right there. And what is the element is gallium. Gallium is in the same family with indium, so it's right here. Okay. Now, let's think about relative to the rows first. Which is easier to remove an electron? Something that's near the bottom of the chart or something that's near the top of the chart? Well, let's remember where the metals are. here is the dividing line with the metals. So if I'm looking at this family, for example, the one that was to have the lowest energy need to remove an electron would be the one that's the most metallic, the furthest away from that line. So if I'm going down, these two should be lower than these two. Now, if I'm going across the periodic chart, what happens to size when you go across? They get smaller, right? Okay. So that means the one that's smallest is going to have the highest ionization potential. So both of these are going to be higher than these. And of these two, this one's going to be the highest of them all. So we expect the one with the highest first ionization potential in this group to be bromine. And that would be response B on the test. And number 31, that's 30. Number 31, rank the following order, decreasing, increasing electron something or other. This was not a good, electronegativity, okay, electronegativity. And again, we're going to look at the periodic table. We got arsenic. Arsenic is right there. We got sulfur is there, and selenium is there. So we've got sulfur on the top. We got sulfur here. We've got selenium is right under sulfur, and arsenic is right beside selenium. Now, I want you to remember for electronegativity, the quick and dirty way. Here's the noble gases over here. These two are closer to their noble gas than arsenic is. So these two are going to be more electronegative than arsenic. So right here, I already know arsenic is the smallest. So the correct answer has to have arsenic here like that. Okay, I can eliminate C and D. Only A and B have arsenic in the right place. So then now, which of these two would be largest? The electronegativity increases going up. So sulfur is going to be bigger than selenium. They're both the same distance from their noble family. So sulfur is going to be the largest. So the largest one over here has to be sulfur, which means selenium is the one in between. And so the answer I want is ASSES. ASSES, that's A on the exam. Okay, moving right along. 32. The ground electronic state for a +3 ion is this, and identify the element. Now, there's a quick way to get to this, but let's go back over. You need to see this to get to this answer. Now, instead of trying to take each one of these and do the electron configuration for it, I'm going to take the quick way. I'm going to add up all of these electrons, and I'm going to see how many electrons there are. And so I'm just going to add all those superscripts up. So it's 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 10. Now, did I do that right? Let's look. 2, 2, 6, 2, 6, 2, 10, 6, 2, 10. Okay, so the number of electrons that I have in here is 48 electrons that are in the it's going to be a metal, and it's a +3. Well, maybe I think it's a metal. So it's a +3 ion. It's still got 48 electrons. How many did it have before? I'll add 3 more to it. It'd be 51 electrons in the original atom before it lost. So it ought to be element number 51 if I haven't made a mistake somewhere in my addition. That says it should be antimony. And I see antimony. This is SB. And antimony is response B on the test. So that's going to be the correct answer. Now, if I wanted to do that to double check, I wouldn't on a test because it would take too long to do it. But instead of trying to do all of those electron configurations, if I can determine how many electrons is in the neutral atom, I know that's also how many protons it has. So you see, by taking use of that information, I get to an answer real quick. It would take a long time to do the others. And what you might try to do is do each one of them and see which one was the correct answer. But that would take you a lot longer. Now, number 33. What's the total number of electrons that can have quantum number n equal to 3, L equal to 1, and M equal to 0? M equal to 3, L equal to 1, and M equal to 0. Well, if L is 1, it's a p orbital. +1, 0, -1 for M. So it's going to be, N is 3, so it's actually going to be the 3p orbital. And I'm talking about how many electrons can be in that one. Well, one was spin up and one was spin down. So the answer is 2. They could have 3, 1, 0 plus 1/2 and 3, 1, 0 minus 1/2 for its quantum numbers. And now number 34. What's the correct abbreviated notation for the electronic ground state of chromium +4 ion? Okay, now, if you're doing a positive ion, you must first do the negative ion, the neutral, and then take electrons away from it. So let's first do chromium. Chromium is right there. Its noble gas is argon. And then what do we do after we get to argon? We go argon is 4s2. After that.
Dr. Pearson?
Yes, you need to see. Yes, I'm sorry. I got it. Here we go. There we go. So chromium is this element right there. Its core is argon. After argon is the 4s2 to get the calcium. And then we're going across to chromium. 1, 2, 3, 4. Uh-oh. Now, if this asks me for the electron configuration here, that should have set off a flare when I did the 4s2 3d4. That is that exception. It's going to be 4s1 3d5. So I'll go ahead and put it in, although it won't make a difference for this problem. Now, what I do, let's think about what this atom looks like. Way down in the middle is the argon core. Then around that argon core, there's a 3d orbital with 5 electrons in it. And outside of that, there's a 4s that has 1 electron in it. Now,
Yeah.
this is what the chromium looks like as a neutral atom. Argon core is this part right here. Then it's got a 3d with 5, a 4s with 2. I put the 4s outside because the n equal 4 is a bigger orbital than n equals 3. The size is determined by the n value. So the 4s electron is on the outside. So here comes some other nonmetal. And the nonmetal is going to come in and bump into that and take off. In this case, we want to take off 4 electrons. So what is it going to do? It's going to get these two first, this one first, and then it needs to take 3 more. So it's going to be a 3d2 left over. So chromium plus 4, its configuration is argon 3d2. And actually now, if I were doing this, I would separate them into 2 separate orbitals because they would be. You wouldn't be paired up in one of the 3d orbitals. So it'd still have 2 unpaired electrons. But if you look at your answers for that one, that is response A. So that is the correct answer. And let's see, I should probably share that with you because the next one we can answer from over here. Okay, so we're looking for number 35. What does 35 says? According to Hund's rule, how many unpaired electrons would be in Ce? Okay, we've got to get cerium, and cerium is way down here. Oops, I have to show it to you. Cerium is right there, that element on the periodic chart. So let's do it. Cerium. Now, that's element number 58. So it's going to have a core 58. It's greater than 58 and less than, so it's xenon, not radon. So it's Xe. That is number 54. And then we're going down to number 55 over here. That's going to be 6s. It's going to put 2 electrons in it to get to barium. So 6s2. Then we go to 57. That is in the D set. And it's 3, 4, 5d. And it's going to have 1 in it. And then we're going to go to cerium. And that would be the first one of the 4f. So that's going to be 4f with 1 in it. So the question is, how many unpaired electrons would it have? Well, everything else is paired up except these. So there would be 2. And that's response D on number 35. Number 6. Which of the following molecules is polar? I need to share my screen with you again. Okay, which ones are polar? Okay, well, 36. This is a carbon compound that we can pretty easily do. Carbon needs 4 bonds, and it turns out this compound has 4 bromines. Bromine needs 1 bond each. So it's going to be a tetrahedral structure with all 4 things attached the same. That's not polar. CO2. We can do it the same way because carbon has to have 4 bonds and oxygen each needs 2. So I can do that one quickly without doing the math part of it. Okay, it's going to have, need to show it to you. Well, let me write all 4 of them down. So this one is C, and B is Xe, F4 is B, and OCl2 is D. Okay, I've got them all written down now. I'll let you see what we're doing on the screen. So carbon needs 4 bonds, bromine needs 1, and 3 lone pairs. So the structure we're going to get, show all the lone pairs, is this one. It's tetrahedral. four things attached, is tetrahedral, and they're all four the same, so this molecule is not polar. If you replace one of the bromines, say with a chlorine, it would be polar. If you replaced two of the bromines with two chlorines, that would still be polar. If you replace three of the bromines with three chlorines, that would still be polar. But if you replaced all four with chlorine, it would not be. The idea is they're all the same. They're all the same, it's not polar. This is the CO2 molecule, again using the usual bonding structure. Carbon needs 4 bonds, and it would have a double bond to each oxygen. Oxygens are supposed to have 2 bonds and 2 pairs, so this is the structure you have for CO2. Each end of the molecule, it's an AX2, so that's not going to be polar. Both ends are the same. If you changed one of the oxygens, say for a sulfur, it would be. If you change both of them to sulfur, it wouldn't be, okay? It's symmetrical. We can do this one also from the bonding rules. Oxygen is supposed to have 2 pairs and 2 bonds. Chlorine is supposed to have 1 bond. So again, now this structure is tetrahedral. There's 4 things attached. 2 of them are lone pairs and 2 of them are oxygens. So this is going to be polar. So it is polar. And so that actually is my answer, but I'll prove that this one is as well. I'm going to do the math on this one because xenon shouldn't form any bonds. So I need to figure out what it would form. Xenon's in group 8. There's I've got to add to that 4 fluorines, and each one's in group 7. So that's 28 and 4, 7, 28, 28 and 20 and 8 is 36. 36 divided by 8 is 4 to 8 is 32. Remainder is 4. Divided by 2 is 2. 4 and 2 is 6. It's an octahedral molecule. We're going to put 2 lone pairs on. Where could the first lone pair go? Pick anywhere. Let's say it goes here. The other one has to go there. Xenon is going to go here, and the fluorines are going to go here. Now, in figuring whether an octahedral molecule is polar or not, you look at each of the 3 lines that make it up. There's one line. They're the same on each end. It's not polar along that line. There's another line. It's the same thing on each end. It's not polar along that line. Here's the third line. It's got the same thing on each side, a pair of electrons. So it's not polar. So this one is not. The only one it is Cl2O. Number 37. The electronic geometry of SF4. We have to do the math because sulfur should only form 2 bonds. This is showing 4. So 6 plus 4 times 7. 4 7s are 28. 28 and 6 would be 34. 34 divided by 8 is 4. 32, remainder is 2. Divided by 2 is 1. It's an AX4E type. 5 things attached as a trigonal bipyramid. Okay, now we want the sulfur to be here. Now, where does the 4 fluorines go? Well, we first put the lone pair in. It goes in the equatorial plane. Goes there. The 4 fluorines go in the other position. Now, what did it ask me? We already got the answer. The electronic geometry is what we got here. 4 plus 1 is 5. So it's trigonal bipyramid. That's answer A on the test. Now, there is an answer you have to watch out for. It's D, and it's seesaw. Now, that is the molecular geometry. Because if I take off the lone pair and then just look at what's left, what I see is something that looks like a seesaw. So the molecular geometry is seesaw. The electronic geometry is trigonal bipyramid. And in this question, I bolded the electronic geometry because I wanted you not to be tricked by that. 38. Rank the following in order of decreasing atomic radius. And okay, let's see what we've got. We've got phosphorus. Now, I'm going to do the same thing we did a while ago. I'm going to locate them on the periodic chart. So where are we? Phosphorus is right here. So I'll put phosphorus right there. Now, the next element in there is gallium. So if I'm in the phosphorus row, I'll go down below it and over 2. So I'll go below it. I'm going to skip that one. Oh, wait. Phosphorus? Yeah, down here. I'm going to skip that one. That's germanium. And gallium is right here. Now, where's the other element? It's germanium. Oh, it's right here. Right? Yes, this is GE here. Well, that'll make it fairly easy comparison. So we want rank them in decreasing size, atomic radius. All right, now, again, we've got 2 rows. The rule is the further they are up, the smaller they are. So the smallest one is going to be phosphorus. So I want phosphorus to be the last one on the right. And let's see, it is in C. Okay, let me share this with you so you can follow with me on this and see how we're doing. Okay, now, phosphorus is the smallest one, so that means it's either C or D. Now, the largest one is going to be gallium. Oh, I got a missing one. So I didn't put silicon on there. Back up. I need to put silicon on here too. And let's see, where's silicon relative to these? Sulfur. Okay, silicon's right. No, phosphorus. Silicon is right there, right here. Next door. There we go. Okay, now we're good. Now, but still we're okay. The silicon is going to be the next one, really. So I can go ahead and put that in because both of these are smaller, but this one's bigger than that one. So this is going to be silicon. Okay, let's see. I'll just go back and glance at so I wanted phosphorus and silicon. Oh, you know what? We got the answer already. Let's go back and share it so you can see. I'm trying to show you to use the test and use the answers to save yourself time. So when I compared the phosphorus and silicon, I need phosphorus to be the last one and silicon to be next. That satisfies this one. The only one of the others that has phosphorus in the right place is D, and it has silicon in the wrong place. We're done right now. We can get that answer. But if I wanted to get the rest of them, then both of these will be larger. Which is larger, the elements to the left or the right on a family? Well, yes, gallium is going to be larger. It's further to the left than germanium is on the same row. So this does satisfy both of them. But again, what I'm going to do is always go for the largest and the smallest. That's the first 2 comparisons. That's the easiest one to make and the least likely to miss. So do it that way. All right, now we're ready for number 39. And I'll copy the molecule down and I'll bring you over here to look at it. CH3, CH, NH is my molecule, and we want the CCN bond angle. All right, let's go over and take a look and see what we can do. Now, let's look at the way the structure is drawn. The way the structure is drawn is hydrogens cannot be in the middle of a molecule. You don't have carbon, hydrogen, 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 carbon, hydrogen, nitrogen, hydrogen. These three hydrogens belong to that carbon. That's the way we don't put them on that one, we put them on this one. So let's do that. Carbon needs 4 bonds. 3 of them are going to be taken up by those 3 hydrogens. It has to be attached to the other atom, so that has to be a carbon. That hydrogen can't be between nitrogen and hydrogen. The standard idea is this hydrogen, if it's going to be off the line, this atom belongs to that one. So I'm going to put that hydrogen onto this one. Now I have to have a connection to nitrogen. Now nitrogen has to have 3 bonds and 1 lone pair. I'm going to put the lone pair on first so I don't forget it. It needs 1 bond to get to this hydrogen. Now, I need another bond to the nitrogen and I need another bond to the carbon. So that means it has to go there. Now, if I'm looking at my molecule, every carbon has 4 atoms, 4 bonds, and no lone pairs. Every hydrogen is bonded to one other thing. Nitrogen has 3 bonds and 1 lone pair. This is the valence bond Lewis dot structure for this molecule. Now we're asked for the CCN bond angle. CCN bond angle. So this is the central atom I want to look at. What is its VSEPR notation? Well, it's the central atom. It's attached to 1, 2, 3 other atoms. It's AX3. It has no lone pairs. AX3 is trigonal planar. So that's one of my carbons. That's one of my carbons. That's a nitrogen. And that's a hydrogen or whatever. And this is the bond we're talking about. But the angle we wanted was the CCN bond angle. CCN bond angle was this one. All these 3 angles are 120 degrees. So the answer to that one is going to be, well, whichever one has got 120 degrees as the answer. That is the answer. 120 degrees, that's D. Okay. Now let's look at the next one. What am I seeing over there on the side of this thing? Oh, do we give you that structure? Well, okay. That was nice. All right. Okay, moving right along. Molecular geometry of BRF3. Okay, number 40. I think you can see already ways to shorten this test a lot. And that's what we did in dropping down. Okay, bromine is 7. Fluorine, there's 3 of them, and it's in group 7. 21 and 7 is 28. Valence electrons divided by 8 is 3. That's 24. 4 left over divided by 2 is 2. It's an AX3 E2. And what did it ask me to tell me? Molecular geometry. Okay, I need to do this thing then. So I'm going to do 5 things is trigonal bipyramid. 2 of them for the bromine right there are going to be lone pairs. The fluorines belong to the other positions. And now leaving off the lone pairs, the shape of the molecule is the T shape. So it's a T-shaped molecule. And that is response D. All right. And 41. Rank the following in order of increasing metallic character. And again, I'll copy these down and take you over to the periodic chart. We're looking at silicon, bismuth, and selenium, and we want metallic character. Okay, so let's go back over there so we can see the periodic chart and sketch where they're located. Where silicon is right there, so it's under carbon, so let's put silicon here so I can do things on each side of it. Okay, bismuth, where is bismuth related to silicon? It's way down here. So we want to go down 4 and over 1. All right, silicon, 1, 2, 1, 2, 3, 4, and over 1. That's right. So bismuth is going to be right there. And now we want selenium. Selenium relative to silicon is going to be on the next row down and skip 2 this way. So silicon is here. So I'm going to this row and I'm going to skip the first one and go to the next one. That's Se. Now let's just be sure if sulfur here, I go down 1 row and over 2, that gets me to selenium. And then I go down 2 more, get to this row and over 1. Okay, I think that's good. Now, what I want to do also is write the, I think I can get it without it, but the metal to non-metal dividing line goes across the periodic chart in this area like this. Okay, that's the metal to non-metal dividing line. Well, you know, just looking at that element is clearly in the metal side, the others are not. So that one's not going to be as metallic as this. So the least metallic, what did the question say? I have to look back at it. And it says increasing metallic, oh, I said it right there, increasing metallic character. So the most metallic element should be the one on the right. So now I can answer it. The most metallic element, it's increasing metallic character. The most metallic element is bismuth. Now, so that one's going to be more metallic. Now, what about these two and these? Now, this one is right there. It's just across the line from the metallic character elements. We've got, and so this one, yes, I'm right. There's the dividing line. It goes aluminum. Aluminum is metallic. Yes, yes. Okay. So this one is going to be more metallic than this one. This one will be the least metallic. So we want Se and Si. That should be the order that we get them. So let's go back and see what answer that corresponds to. So we want Se less than Si less than Bi. That would be B answer on the chart. Rank the following in decreasing acid strength. Now this one's going to be quick and easy. 42. And we've got HI, HCl, and HF. And we want to rank those in order of decreasing acid strength. Okay, let's go back and take a look over here, and we can do that pretty easily. If I'm looking at these acids, remember the 6 strong acids? What were they? HCl, HBr, HI, HClO4, H2SO4, HNO3. There was 6 of them. HF is absent from that list. It's not a strong acid. It's a weak acid. So if I'm looking at the periodic table, fluorine is up here. And in this family, there's chlorine and bromine and iodine. Now make the acids of these. One of the things about the periodic chart is that there are regular trends in behavior. So if these 3 are strong acids, and this is a weak acid, what's the order of acid strength? Well, this is the weakest, and that would be the strongest. So the weakest acid would be HF, and the strongest one would be HI, and HCl would be in between. So if we go and take a look to see which one's got that order, we got the answer then. Okay, so the weakest acid is HF. That'll be the one farthest on the right. That's either B or C, but HI would be stronger than HCl, so the correct answer is going to be B. And 43, we want to do the number of sigma and pi bonds, and oh my goodness, maybe I need to go back to 100%. The pictures are that big. Okay, so here we go. I'm looking at this molecule and I'm saying, okay, it's all strung out here for me. I have to have a sigma bond between every one of the pairs of atoms. So that's a sigma bond, that's a sigma bond, that one and one of these, that one, and one of these. So I got 1, 2, 3, 4, 5, 6, 7. I've got 7 sigma bonds. You're with me on the exam? So it could be either A or C. It could not be B or D. How many pi bonds does it have? Well, it's got 1 here and 2 here, so it's got 3. So it's 7 sigmas and 3 pi's. That's going to be response C. So we're good. What is the hybridization of the middle carbon atom in that molecule that's shown up there? Well, there's 3 carbons, and I take the middle one to be this guy right here. So let's see what its VPR, no, VSEPR notation is. Let's, you're going to write down A. That is the carbon atom we're looking at, this one. How many other atoms are attached to it? There's 1, there's 1, and there's 1. So it's an AX3. So it's got 3 bonds to it. And now let's go to our periodic table to get hybridization. We're possibly using S, P, and D. We use them in that order. And I need to put on 3 bonds. So I need 1 here, 1 here, and 1 there. So I need an S orbital and 2 p orbitals to give me the 3 hybrid orbitals I need to attach the 3 x's onto A. So it's sp2 hybridization. It's sp2 hybridization, and that is C. Now we're ready for number 45. A newly discovered solid on the surface of the moon is detected as being red crystals having a characteristic odor and a melting point of 71 degrees C. Its non-conductive solid could be best described as what? Okay, we're thinking about the kinds of solid molecules, compounds we could have. They could be molecular compounds. They could be like water, carbon dioxide, something that would be a covalent compound. It could be ionic, which means it's positive ions and negative ions. It could be metallic, and it definitely is out of the world. That's not the right answer, though, by the way. Okay, so if it were ionic, let's think about that. What would be the melting point of ionic compounds? Typically, it's very large. This stuff melts at 71 degrees, so it's not ionic. Now, is it metallic? Well, it could be metallic because we have a liquid metal, mercury, and we've got other metals that are, they usually tell everybody that mercury is a liquid. You can hold it in your hand. It's not a good thing to do because it's toxic, but you could. Gallium will melt in your hand. If you were to pick up a piece of gallium metal and hold it in your hand, it would melt. And I usually tell people that cesium will melt through your hand. It's so reactive, it would burn its way right through your hand if you held it in your hand. So you do have to know how to handle cesium. But most metals have much higher melting points. It is possible that this guy could be a metal. Let's see if we can eliminate the metal. It's a non-conductive solid. Okay, it's not a metal. Because if it were a metal, it would conduct in the solid state. So we've eliminated the other two possibilities. It has to be molecular, and that does fit. Molecular compounds would possibly have a low melting point, like 100 degrees, and it wouldn't conduct in the solid state. It didn't tell you here, but it probably wouldn't conduct in the liquid state either. If you melted it, it probably would not conduct an electric current if it's molecular as well. Now the color depends on the elements that make it up and all this kind of stuff. So I can't tell anything more, but I can eliminate the other answers. The only one that still makes sense is A, molecular. Now, number 46, the bright line emission spectrum of hydrogen is caused by, well, you know the answer to that. We've talked about that and done labs on that. It's electrons going from higher energy levels, discrete higher energy levels, to the ground state. So let's see if we can find that up here. Intense molecular collisions brought about by heating the gas to a high temperature. No. Electronic transitions from higher potential energy levels to lower. There you go. That's it. Interaction of electricity with the hydrogen atom. Nah, that does happen, but that's not why you get the line spectrum. Nuclear transitions, no. Nuclear transitions do not emit visible light. There is a case where they can emit X-rays, but we can't see that. So it's not going to be a colored line spectrum, even from X-rays. Okay, so 47. Well, for that answer then, it was B. 47. Rank these increasing ionic character. Okay, I2. I'll copy them down over here. 47. We got I2. We've got SnO2. And we got LiI. Okay, now, Let's go over and take a look at these things. And we're looking for increasing ionic character. Okay, so
Dr. Pearson,
yes.
silicone, not tin.
Oh, it's silicon. You're right. Thank you. I'm getting a little frayed around the edges.
I totally get it.
Okay, here we go. All right. Now, ionic character. Well, to have ions, you have to have ionic compounds. You have to have a metal with a non-metal. I've got one of my answers already. Increasing ionic character means I2 has to be the first one over here. We could go over the exam, and I would if I were taking it, see what I've eliminated. Now, the other two, this is clearly a metal, and this is clearly a non-metal. This is two non-metals together. Metals with non-metals are more ionic. So I got the lithium iodide is going to be the most ionic of the bunch, and then that would force silicon dioxide to be in the middle. Okay, so that should be the answer. And at number 47, and the answer should be iodine is the least. So you see the first answer we did would have eliminated A and B. And lithium iodide being the most makes it D. So this answer 47 is D. And 48. The hybridization of nitrogen in NO2 minus. Yeah, I can think of lots of ways. This same question's been asked 2 or 3 times already. And we've got hybridization in NO2 minus. I do that sometimes on practice exams to have you practice the same thing over and over again. That sometimes is hard. Okay, nitrogen's in group 5. Oxygen, there's 2 of them. It's in group 6. And it has 1 more electron. 12, 13, this is going to be 18 valence electrons. Divide by 8, that's 2, that's 16, and 2 divided by 2 is 1. It's an AX2E. It has three things attached. So if I'm doing hybridization, I want hybridization for 3 things attached. So if I do the s orbital, 1, 2, 3 p orbitals, we have to consider d, but we're not going to get there. S and p. So I've got 3, that's 1, 2, 3. That's going to be sp2. That's the answer to that one. And we're 48. sp2 is C. 49. Predict the formula for the ionic compound between gallium and sulfur. So we got Ga and S, and this is 49. Let's go over the periodic chart and locate them. So gallium is right here, and sulfur is right there. So gallium is more metallic. Further down, it's in the metal group clearly. So gallium ought to be the front element in the formula. What charge should it take? Should be the same as its group number up here. So it should form a +3 ion. Now, if I'm at sulfur, what should it be? It's in group 6. So 6 minus 8 is -2. So it would get a -2 charge. So I want a total of 6 charges. So I'll need 2 galliums. And I need 3 sulfurs. So the expected ionic compound of this gallium sulfide would be Ga2S3. And that would be Ga2S3 would be response C. Number 50, an element 10 has how many valence electrons? No, that's a gimme. 10 is in group, it's in group 4, so it's got 4 valence electrons. So we can get that one easy enough just by looking on the charts, number 4. So that is C. 51. Okay, cut to the end of this thing. Very good. How many lone pairs of electrons are there on the oxygen atom in OF4 2-? We've done this kind of problem several times also. OF4 2-. Okay, let's see. I don't like that one, but I'll duck my head and do it. I'll tell you why I don't like it in a minute. So this should be 4. I've got 6 valence electrons from oxygen. I've got 4 fluorines in group 7, and I need 2 more for the charge. 28, 30, 36. This is 36 valence electrons divided by 8. That's 4. 32. 4 divided by 2 is 2. So it's an AX4 E2. And it said how many lone pairs? We've already got the answer. Right there, it's 2. So for 51, it's response B. Now I'll tell you why I don't like it. Because there's no way in the world oxygen is going to have 12 electrons around it. Oxygen is in the first row of the periodic table. None of those elements can ever have more than 8 electrons around their outside atoms. So if I'm writing this question, I'm going to make that S F4 2-. It's the same math, but it's realistic. That is what would happen. OF4- would not happen. But if it did, it would have 2 unpaired electrons. 52. What's the VSEPR notation for the nitrogen atom in this molecule? And I think solved the mystery of these formulas down here. This is probably put there so that we could see what it looks like and work out the answer. It's probably would not have been printed if this had been an exam. So you do need to know how to draw the structure. So I'm going to come over here and do that with you because that is something that needs practicing. Oh, I jumped the gun too quickly. I see that end and I grew up on a farm. The worst time of the day to plow with your horse was near supper time, because every time you plow toward the barn, they're going to want to run. So I saw the barn here and I took off for a run. Okay, it's CH3, NH, OH. Now that's the structure. Let's go over here and let's actually draw what they show on the picture there. These 3 hydrogens belong to that carbon. So I'm going to put them on like that first. Now the carbon needs another bond and it'll be to that nitrogen right there. Now nitrogen has to have a lone pair. So I'm going to put it in before I forget. That hydrogen has to be off to the side. So it has to be there. And now the next one is going to attach the nitrogen to the oxygen. I'm going to put the 2 lone pairs that are required for the oxygen there and the other hydrogen here. Okay, now I've got my structure. And let's see, what did it ask for me to do? I didn't write that down. Oh, it wants the VSEPR notation of the nitrogen atom. Okay, now let's go back. This will be easy. Okay, the nitrogen, we're going to call that A. How many atoms are attached? 1, 2, 3, AX3. How many lone pairs? 1. AX3E then is the VSEPR notation for that particular atom. And that should be the correct answer.
Dr. Pearson,
Yes.
technically, wouldn't nitrogen always have that VSEPR notation since it's in the first row?
It's going to have one lone pair, but it might not. You could have nitrogen like this. It could be bonded, doubly bonded to some atom and singly bonded to some other atom and a lone pair, in which case it would be AX2E here. So
Okay.
it's always going to have E.
That's it. Okay.
So that might come in handy. Yeah, if you took that as a requirement, you've eliminated B and D on this test. See, those both have more than one lone pair on nitrogen. It's not going to have more than one lone pair on nitrogen. It's always going to be one in these kinds of structures. Okay, I'm going to stop the. I'm going to pause the recording and